Okay. Right, so thank you for coming. I'm going to talk to you about, well, first asymptotics in Isabelle in general, and then the recent stuff I've developed for automating some of it. So first of all, I'm going to talk about what methods we have in Isabelle for describing asymptotics. So Johannes already talked about this yesterday, very good in the filter stuff yesterday. So essentially we have this concept of filters which describe neighborhoods in a sense. So you have like the neighborhood around a number, a real complex number, and you have the neighborhood around infinity, or you have the neighborhood around complex infinity, so things like that. It's always kind of a neighborhood of, well, not always, but that is what I use it as, the idea of a neighborhood of something. And then, of course, with that you can also describe limits. So a limit just means that if you take one of those neighborhoods and you map it with a function, then you get something that is in a sense finer than the other neighborhood, and that means that thing goes to the limit. So for instance, if you in mathematics you had something like f goes to c, where c is some real number or something, and as x goes to infinity, then Isabelle would write this, where this is the neighborhood filter around c, and this is the filter that describes the neighborhood of positive infinity. That's pretty straightforward. And so what I then introduced is also Landau symbols to relate functions with respect to their asymptotic behavior. So in just like in normal mathematics, you can write something like x is element of big O of x times ln x. And also, so this is essentially, this means that this holds as x goes to infinity, but you can also look at other neighborhoods, like you can specifically say, okay, I want to explore the situation as x tends to 0, and so in this case, it's in a way reversed, so suddenly x squared is element big O of x as x goes to 0, so you can also write that. And then recently I found another curious little thing, which is in textbooks you often read things like quicksort needs O of n squared or O of length of x squared comparisons to sort a list of, the question is, what does that actually mean? So usually you mean like worst case complexity. The worst case complexity, the worst case cost of quicksort is big O of this thing. And there's a nice way to write that down with filters. Namely, you can write the costs of quicksort are element big O of the length of the list squared with respect to this filter where length goes to infinity. You can just write it down like that, and it means exactly what this intuitive thing means here above. So it's a very flexible framework, this filter stuff. Okay. By the way, just feel free to interject questions at any time. This is not terribly important. It's just like to give you a short overview.
So this bracket at, that's Isabelle, and the one above is math.
Well, the one above is also Isabelle. You can also write this in Isabelle. So essentially, when you leave out the bracket stuff, then it defaults to at top. Because like essentially, like in the beginning, we only had this in Isabelle, and then I thought maybe I should generalize it to allow arbitrary filters here.
Yeah.
So I introduced this and left the old behavior kind of as a default. Because it's also my experience that usually when people talk about Landau symbols, they kind of mean the limit to it going to infinity implicitly. It's my experience, especially like in algorithms context, of course.
They also have to 0, but you too. So
yeah.
And the definition of O in Isabelle, you are still giving it, or we are to infer it from this slide.
I wasn't going to give it, but it's like maybe I should write it down. So essentially. F is element big O and filter F. G, if and only if, what was it? There exists some c greater than 0 such that eventually
should that be G of x? Where does this little f go? Oh no, it's this f, sorry. Yeah, I found it.
Yeah.
And eventually, of course, means that this predicate is in the filter.
So essentially, that this property holds in some neighborhood described by that filter. That's the idea. So essentially, if you have here at the top, it just means that for sufficiently large x, this will always hold. And yeah.
So,
and of course, small o and big theta and everything are defined analogously.
so there must exist a neighborhood in the filter such that for all x in that neighborhood, this condition is true, is it?
Yeah.
Yeah. Okay.
Yeah.
Just trying to.
I mean, essentially, a filter is just a set of sets, right?
Yeah.
What it says is that essentially the set of all values x for which this holds is an element of the filter.
I would guess the crucial thing is the telescoping property that once you got the one for which it's true, it also continues to be true as you focus in even more. And that's what the crucial property of a filter, and that's why it matches your intuition.
Yeah, what is the definition of filter again? A set of sets such that?
Well, it has to contain the power set, right?
No,
sorry, the empty set.
No.
Sorry.
Filters are closed under, so it's a set of sets which are closed under intersection,
Finite intersection type.
finite intersections, or binary intersection. And if x is in the set and y is a superset of x, then y is also in this filter itself. And filters are not empty, so it is at least one set, or you say it's the entire set, your x, or your separate set is also in the filter.
Very good.
Yeah.
So I must admit that I never really thought about this very much myself. I just use this because it's useful to me, but I never made any very large effort to understanding all
And this on top filter?
But at top,
Or at top, yeah, sorry.
it's just like you assume you have a order on your elements, and you say a element is in the filter if there exists a element n such that there's that all elements bigger than n are also in the set. So let's say S is at the top. If n is in the set S and all bigger elements in n are also in the set.
So yeah, this is described by the co-map operation that Johannes also talked about yesterday. So it's like the contravariant map operation on filters. And these filters are really nice. Like they form a complete lattice, even a distributive lattice, and so you can do a lot of nice things with them. Okay. Right. So then one of the first things I did with the Lambda symbols was I introduced some automation to make the reasoning at least a little bit more comfortable in Isabelle. So essentially, for instance, I wrote a simplification procedure that essentially, when you have big O of some sum of elements, so this is not only two elements, but it works for, in principle, it works for arbitrarily many elements. It tries to figure out whether it can prove automatically that for some element of that sum, like this G, is dominated by some other element of the sum, like this F. And if that's the case, it just throws away the G and simplifies this to big O of F.
So for little o, you also have such a form?
Yeah, for little o, it's essentially the same, except that you have a universal quantifier here. So in a sense, they are dual. Yes. Right. So, and another thing is that, okay, so this one is only valid if it can also prove that H is eventually non-zero, but then you can essentially cancel elements out of products. So I have a simplification procedure that analyzes products to find common factors, then tries to prove that they are non-zero eventually, and then it just cancels them out. And I mean, these are like operations where any mathematician would just do them automatically by hand and not think about it. And if you have a theorem prover, you also don't want to think about this if possible. You just want it to go away automatically. And then a little more specialized operation, but which is also very useful, is if you have something like, so this, you have some power of x, and then you have some power of log x. So any positive power of this thing will always grow much more strongly than any power of this thing. So essentially you get a kind of a lexicographic order. So if you have a product like this and a product like this, and you want to know if this thing is in big O of this thing, you can just essentially lexicographically compare the exponents, and essentially I have a simplification procedure that brings those things, anything that can be brought into this form, and then rewrites it to give you this thing. And then if those things are constants, then this can just be shown automatically. So whenever you have any product of powers of logarithms, and you want to show some big O relation, and maybe you have the sum of them, then the combination of all these simplification procedures will essentially figure it out in the background by itself, and you just have to write by auto or by simp, and Isabelle's automation will figure it out for you. And that was a huge help for me in a project that I worked on, which I will talk about briefly later. And yeah, it's just always nice if you can automate things that are obvious to a human, and because if you want to prove any particular instance of this by yourself, by hand, you would have to prove the limit or something, or find like the constant like this, and it just gets very tedious, and you have like a lengthy messy proof of something that is completely obvious to you. So of course you want the computer to be able to figure this out by itself. Okay.
Could I clarify, is that just for that exact pattern, or is there a more general schema when one thing dominates the other?
So essentially I formalized it in a relatively general way so that you could in theory plug in more functions with this property, but in practice the only reasonable set of functions that I found was powers of logarithms, essentially. But also powers of iterated logarithms. So it's essentially anything that is of the form some iterated logarithm to the power of some real number.
Not exponential functions. I mean, they are sort of similar nature, of course.
Yeah, but the problem with exponential functions is if you only allow something like x of x and x of x and so on and so forth, then you could do that. But if you have more complicated expressions under the exponential, which you often have, then it gets messier.
No, I meant this thing that exponential always grows faster than any polynomial, so you would also get a sort of dual kind of lexicographic thing.
Yeah, as I said, you can do that relatively easily, but the problem is that the question is what class of functions do you allow? Like for instance, you can allow you could say, okay, I allow anything of the type e of x, so e to the x.
No,
or
e of a times x probably.
Okay, yeah, but then yeah, you can. I thought about this, but I couldn't find a suitably general.
Yeah, times a polynomial, and then and if the a of the one is bigger than the other, then the polynomials can be what they like, and it dominates. And if the a of the two sides are equal, then you have to look more closely and study the polynomials.
Yeah, as I said, you could do that, but I didn't do that in the end because that would just cover like one specific case, and more complicated exponential expressions wouldn't work. And so that's why, because the question is what's now if you have something like 2 to the x, and then later you have 3 to the x and e to the x, then it already gets a little bit more complicated. Now if you also have x squared, then it gets even more complicated.
2 and 3 to the x you must rewrite with everything to base 2.
Yes, you can do that, yeah. So the point is, but then you have the question what happens when you get this. But I will essentially discuss a completely different approach later that can handle these things. Like that's the main part of my talk. This is just like the preliminaries to show you like the first little baby steps that I made. Yes.
So what kind of theorems are interesting? So the area of the, for example, are you mainly like focusing on proving some bounds for the algorithm or something like that?
Well, that is one of the applications that you would like to have a library with which you can talk about runtime complexity of algorithms. Yes. So I'll show a few little applications in a bit. Okay. Right. So yeah, as I said, so things like this you just write by simp and they go away, which is what you want, of course. And you can see that like to do this thing, the simplification procedures work together. Like first the first one will essentially use the third one to show that this thing is dominated by this thing, so you can just remove that thing. And then you're left with this thing is elementary of this thing, and then you can again call this simplification procedure and it goes away. Okay, so just to show you a few little applications here. So the first major thing that I did is I proved the acrobacy theorem, which is a generalization of the well-known master theorem, where you have some divide and conquer recurrence, like you get when you analyze divide and conquer algorithms, like Karatsuba multiplication or merge sort, or I think the Fourier transform also falls under that, fast Fourier transform, and things like that. And essentially, the acrobacy theorem tells you what is the big O complexity of that function. So it's a relatively powerful method for these divide and conquer recurrences. I proved the Euler-Maclaurin formula, which you can use for estimating sums with the help of integrals and the other way around. And I also used that to show the complete asymptotics of the factorial function and the gamma function and the polygamma functions and the error function and the harmonic numbers, so it can do all these nice things with that. And I analyzed the average case complexity of quicksort, so it's like the usual textbook result, you will know it, which says that if you have randomized quicksort, then the expected runtime, the expected number of comparisons is n log n, and if you have a deterministic quicksort and you feed in a list in random order, then the expected complexity number of comparisons is also n log n. So that is something you can easily prove like that. And also I've showed that the lower bound that any comparisons, so any sorting algorithms that relies on comparisons requires is big omega of n log n. I mean, like pretty much these things are not difficult results in a way. So these were just like kind of proofs of concept to show that the theory, the library I developed can handle these things and can work with it quite well. Yeah, and I also I did a little bit of analytic number theory where I started formalizing a textbook on analytic number theory to show these nice results about what is the average number of divisors that an integer has, and what is the average number of co-prime numbers of an integer, what is the average density of square-free integers, things like that. And you can also you can do this very nicely with these Landau symbols. Okay. Any questions so far? So that's just a brief overview. So the problem that I ran into is that sometimes proving asymptotics in Isabelle, and I would guess probably all.
Maybe one question, but you might come to it later. Like these asymptotics, they also appear in terms usually, although strictly speaking not legal, because the whole thing is a set of functions, and then they say, yeah, we gloss over that, and it means this and stuff. And but you have to be careful because equal sign is no longer symmetric and so on. I mean, do you have any of that notation-wise?
Actually, long before me, Jeremy Abigail introduced notation for that, and he wrote like, I think it was something like F. Something like this. And it means something like.
Equals always just element of.
Yeah, so yeah, this thing is essentially just element of, and this is like plus lifted two sets. Where this left hand side is a function and this thing is a set. And then he also lifted the plus operation onto sets in the obvious way. So you can also write something like plus O to the, I don't know, H prime or something like here. But I didn't really use that myself very much. So the library I developed, you can use my library with this notation as well, but I haven't really proven a lot of useful lemmas about it, and I never really quite used this notation, but it's still on my to-do list to figure out whether maybe I can adapt my library, which I mean prove some useful lemmas about the connection of my Landau symbols with these operations to make it more usable, because I mean, this is something that might make reasoning about these functions a bit easier. I'm not sure yet. But yeah, and as you already saw with this bracket thing here, the notation can be a bit cumbersome, because normally, like a normal mathematician would simply not write this part here. They would just kind of implicitly always in the background have the limit that you consider actually. And yeah, if you do like a theorem proof, then the notation gets a little bit more cumbersome because you always have to annotate everything. Okay, yeah. So as I ran into this problem that in practice, proofs of the asymptotics of concrete functions in Isabelle are often relatively ugly. So if you have like a concrete function, a real function, and you just want to show this thing tends to this limit, or this thing is elementary figure of this thing, it gets pretty ugly very fast. And as one particular example, which I ran into when I proved the Acrobacy theorem, I have this nice thing. So essentially, this was one of 4 asymptotic inequalities that I have to prove. I say inequality because essentially I only needed that this term is eventually positive, essentially. And yeah, the original author said that, yeah, well, this is trivial, you can just Taylor expand it, and I stood in front of it. I had no idea about it. I still have no idea about asymptotic analysis, but I stood in front of this and I was like, yeah, Taylor expand what exactly? What with respect to what? And I had no idea. And then I asked on Math Overflow, and I got a very helpful response, very brief response. So it still took me about 1 or 2 weeks afterwards to figure out how to prove this and how to do it in Isabelle. And in the end, it was like 700 lines, and it was completely unreadable and very messy. And I did a lot of refactoring afterwards and reduced it to maybe like 300 lines, but it was still pretty unreadable and very ugly. And I thought to myself, yes, so essentially in Isabelle it would look like this, pretty much the same thing. And I thought to myself, well, I don't want to write 700 lines of proofs. It's not even 300 lines. What I want to write by magic, and then it just goes away. And well, the thing is, computer algebra systems can kind of do that. I write sort of because you have these free variables in here, like the b and the epsilon. I should mention there are some conditions on the b and the epsilon, so these have to be sufficiently nice for this to actually hold. But computer algebra systems, in theory, they can handle free variables. In practice, I found that none of the ones that I tried can do anything with these things. So if you just put that in, they either they work for a few seconds or a few minutes, and in the end, they don't give you any result. So I don't know why that is. In principle, they should be able to do it, but apparently they can't. And so yeah, but in theory, like if you have a function like that, maybe without free variables, computer algebra systems can immediately give you the limit of that. And the question is, why can't we do that in a theorem prover? And the answer is, well, we can do that. And for that, we need asymptotic expansions. So I'm going to explain what those are. And as a disclaimer, like obviously I didn't invent any of this stuff, I just formalized it, and I wouldn't even say that I understand it extremely well. And also, I'm not going to show you any of the actual Isabelle code and Isabelle definitions, because I think it's better to strip those down a little bit for the slides to make it more readable. And as for related work, there's this is like the paper that I was mainly working with, and it explains essentially how to expand real functions involving exponentials and logarithms. And this is I think from around the same time with a PhD student, PhD thesis from a Swiss PhD student back then in 1996, I think, who essentially implemented a similar approach in Maple. And this algorithm that he implemented, it was then, I was told that this is also integrated in Mathematica now, and it's one of the many things that Mathematica does when you give it a real function and want to know the limit. Okay, and so first of all, what we'd really like to have is a compositional approach, because those tend to be more easy to prove and to maintain. So essentially what we want is something like, okay, if we have the limit of some function f and the limit of some function g, then what is the limit of f of x plus g of x, or f of x minus g of x, and so on and so forth. And if the limits are real numbers, then it's obvious. It's just, at least for the like plus and the minus and the times, it's just the. But the question is, what happens if you have something like infinity minus infinity or 0 times infinity, and then you run into trouble, because if you have something like x squared minus x, then both individual ones go to infinity, and the difference suddenly, well, you don't know. You have to problem is you have to track more than just the limit. You need to know the actual growth of the thing, and even that is not sufficient, because of course you can have something like x squared plus x and then minus x squared. So even if you know kind of the leading term might cancel out, and then you need the growth of the stuff that comes behind the leading term. So in order to decide this question, you really need to know the full asymptotic information of the entire function. You need to know exactly how. You need a very precise description of how it grows. And that you can do with asymptotic expansion. So for now, I'm going to, it's easier if we look at x going to 0 all the time. We'll switch to x going to infinity later, but for now it's x going to 0. And there you have the asymptotic expansions are just the obvious ones, namely it's Taylor expansions. And for instance, for x, for the exponential, you have this obvious Taylor expansion, and for the geometric, this thing has the geometric series. And these things really contain the full asymptotic information. And so what do I mean by asymptotic expansion? Essentially the idea is that these series are, these formal series are an asymptotic approximation that gets better and better. So if you cut off this one of these approximations after some term, then the error is bounded by the next term in the series asymptotically. So yeah, the error that you get when cutting off after the term an is big O of an plus 1. That's just what it says. Yeah, and as I said, they contain the full asymptotic information, and you can just add them and subtract them and multiply them formally. So if you want to know the limit of this thing minus this thing, then you can just subtract the series element-wise, and so the 1 cancels out, and then you have x minus x, x minus minus x, so if you have 2x there, and then you know the limit. And you can do that for multiplication, division, and it just works out. And also you can just read off the limits, because if you have this property that that the error is bounded, then you can always just look at the leading term. And the leading term, as long as it's not, well, you have to look at the leading non-zero term, so to say. And if you have a leading term and it's non-zero, then it just tells you exactly what the limit is. Because in this case, like it would be 1, or if that 1 wasn't there, then it would be 0, because the minus x goes to 0, and the error is of lower order, so it doesn't matter.
So the a's here are monomials or polynomials, or?
The a's here are essentially monomials, yes. So like constant times power of x.
But they could be any other function. You could,
yeah, I will come to that later. Like for now, I was focusing on this easy case where it's just powers of x.
And for multiplication, you have to rearrange the x, I mean.
Sorry?
When you multiply the series, then you have to rearrange the exponents.
What do you mean to rearrange?
Well, if you start to multiply 1 by 1, 1 by x, 1 by x squared, and then the other terms.
Yeah, well, it's essentially just the, well, so far it's just the multiplication algorithm on formal power series. So I'll show the algorithms later, but it's really very simple. So yeah, as you already mentioned, one of the problems is that not all functions can be represented that way. So you have, for instance, if you have the exponential function at infinity, there is no way you can expand it in terms of x. And the same thing with the logarithm at infinity or at 0, because you just have they have essential singularities, and you cannot represent them locally with a power series in terms of x. And the solution to that is a little bit more complicated, so I'll come to that later. For now, let's just consider these very easy expansions where we have essentially a formal series of countably infinitely many terms of the form some real constant times x to the power of some real constant. And of course, we want that the exponents keep decreasing. And yeah, okay, they keep just decreasing. Okay. Yes, and I should mention now that okay, I've implicitly shifted now the situation to x going to infinity, because that makes things a little bit easier in my opinion. So essentially, yeah, now we can have expansions like x squared plus x to the minus 1 and so on and so forth, and that's why we want the exponents to decrease, because then each following monomial will be smaller than the preceding one. Yeah.
You just had this decreasing condition, but they could have asymptotic behavior in the way it decreases unless you have some other condition, so they could converge to say 0. Is that okay?
The exponents, you mean?
Yeah.
I think for me that's okay. This will actually never happen for the functions that I consider. So if you really want these expansions to fulfill nice algebraic properties, I think well, also I think this involves things like differential algebra that I know nothing about. So I was just told that essentially when you want these expansions to have nice properties, then you need to demand more things about it. For instance, that there is this concept of grid-based series where you have this property that the exponents are essentially they are in the span of some finite generating set. So it's like a kind of is it a lattice? I think it's like a grid essentially. Yeah, it's essentially a grid. So that they are form some alpha plus some what should I remember? Some alpha plus some n times beta 1 plus n times beta 2 and so on and so forth. So in practice, this is usually what you want. But I didn't actually have to worry about any of these things because I just I didn't actually need any of that. But in practice, any series that I actually work with will have that property. Yeah.
I wondered whether it might also be just for structuring a possibility of writing like f of x equals g of x plus big O of h of x, where the g then might happen to be a polynomial. And then your already existing tactics should be able to deal with polynomials, and then you wouldn't need the special form that it's one monomial plus another, and that you just expand as far as you like. So you have one polynomial with concrete polynomial plus some asymptotic, and then you have to work the polynomials against each other and the asymptotics.
Yeah, I don't know, because the problem is that I have to manipulate these expansions like algebraic objects, and I don't know in advance how many terms I'm going to need. So yeah, I'm not sure if that would work out. But
No.
yeah, maybe we should just continue now. See you later. So yeah, so the question is now, how can we actually do concrete operations on these expansions? I've showed that we can add them and multiply them, but the question is, how do we actually do that in a constructive way? How do we actually implement it in a way? And so the first idea is, I wrote this now in like Haskell-style syntax, that we view expansions at a possibly infinite list of pairs of real numbers, a coefficient and exponent, and then you can implement negation by just iterating over the list and negating the coefficient, and you can implement addition in the obvious way, where you say, okay, empty list is clear. And then if you have two non-empty lists and you kind of have to merge them, so you have to figure out, are the exponents of the leading term the same? Then you have to add the coefficients, and if one of them is smaller, then you have to put that first, and then iteratively add the remaining list, and so on. So it's pretty clear, I suppose. Yeah. And then you can also implement scaling. So for scaling, I mean that you have a monomial times an expansion. So there you just, again, iterate over the expansion, and you multiply the coefficients, and you add the exponents, and you're done. And then you can also implement multiplication like this. You don't have to understand that in detail, of course, but I assure you that it's fairly obvious. So you just have a recursion like that, and you can show that. And this is intuitively what you want.
So actually, for you, it would be enough to do it. I mean, it's anyway co-recursive, but you only need pattern matching over the first parameter?
Unfortunately not, because I tried that and then it's not productive anymore.
Okay.
Because then, so if I really want a constructor here, and I need this constructor here to make it productive, then I need to pattern matching over both, unfortunately.
So these are co-inductive,
Co-recursive.
co-recursive.
I was going to talk about that later, but yeah, essentially the lazy lists that I mentioned here in Isabelle, they are co-data type, so you can write these things as co-recursive functions. But I should mention that the multiplication already requires this fancy thing called co-recursion modulo friends, because here you have here you have a constructor, that's okay, but then here you have an invocation of the plus operation. And for that, you need that plus is friendly, and you need Jasmin Brochet's fancy co-recursion through friends stuff for this to work out. Yeah, but like intuitively, I think the intuitive specification here is relatively clear, and code data package, that's essentially technical stuff, which I'm not going to go into that too deeply. So yeah, I didn't mention simplicity so far, but essentially the idea is, of course, that you want to prove that if you have an expansion of if this thing is the expansion of a function and this thing is the expansion of a function, then the result of that multiplication operation is an expansion of the product of the two functions, and you can show that by co-induction essentially. So I think I'll go into that a bit later. And now I want to show you another thing, which is power series expansions. So if you have essentially, yeah, it's clear that a lot of functions, interesting functions, have local power series expansions around 0. So you have a function g, and it has series expansion for in some positive radius of convergence around 0. And the thing is now, if you have a function that goes to 0, then you can of course just substitute that function into that g, and you still get a valid expansion. And you can also rewrite this by pulling out the first coefficient, and then you have this thing. And now if this f also has an expansion, asymptotic expansion like we talked about before, then you can do the same thing for the expansion. So we have, this is the coefficient list of the power series expansion, and this is the asymptotic expansion. And then you can just copy this down here, and now you've defined what it means to substitute a function with an asymptotic expansion into a power series expansion. And why is this useful? Well, because now we can implement the multiplicative inverse. So if we have a function f, and we just assume that it's in the form some leading term that is non-zero and some tail, then essentially we can write it like this, where the g is of lower order and has the expansion xs. And then we can rewrite this a little bit, and then it looks like this. And then we can, of course, just, if we wanted the inverse of that thing, then it's just this thing, minus one, to the minus 1, and we have now this. And this is now very nice, because this thing is a monomial, and this thing here has is the geometric series, essentially. Well, it's something substituted into the geometric series. And so we can just implement the multiplicative inverse like this. So we scale with that monomial here, and then we substitute xs scaled again with this monomial into the power series of the geometric series. So this is not just the geometric series, it's like 1 minus x plus x squared minus x to the 3, and so on and so forth. Right. Okay? And
sort of clear. I mean, there's this theory of formal power series where they have this inversion formula which looks like this. Then the constant coefficient must be non-zero, which we also have because it's c to the minus 1. But then it's not clear with the convergence. It may or may not. I don't know. Are there good results, like when this thing converges?
Well, I'm not using functional inversion here or anything. This is a completely like by f to the minus 1. I mean I don't mean functional inversion. I mean
no, I mean 1
inverse.
over. But even so. I mean, these expansions are only valid for, I mean, they have this radius of convergence, so they may sometimes not hold.
Well, the power series, I don't require the asymptotic expansions to converge at all. I only require the power series expansion that I substitute into to converge, and this thing, of course, converges for x smaller than 1. Well, the norm of x smaller than 1. So I assure you that the convergence really isn't any issue here.
So what's the meaning of an asymptotic expansion then?
Well, it's that the thing that I explained before, that if you cut off after a finite number of terms, then the error that you make is element of big O of the next term. So if you have something like f of x, g of x plus h of x.
So it's not power series as such, I see.
Well, I mean, it is a power series in a certain sense, but it's just not a convergent one. Well, and not necessarily a convergent one. So the result that you have is that essentially f of x minus g of x is element big O of h of x, for instance. And if you also take in the h of x into the sum here, then it's big O of L of x. So you get asymptotically better and better approximations. This is also why you can cut off, why you can read off the limit of the first term. Okay.
And then with the inverse, don't they then go in the other direction or something?
No.
The powers?
No. Works out very well, I show you.
Because here the geometric series, then the powers go up like x squared, x3, x.
Yeah, but once you substitute, okay. The thing is, I should probably. So as I said here, if you substitute something into the power series, of course that only works out if the function goes to 0. And what that means in this case is that the leading exponent of the expansion is negative.
Oh yeah.
And then if that is the case, then you also have you always have something then you essentially always have negative exponents here, and if you take negative exponents to the end, then it's still negative, and they still go to they decrease.
So f of x goes to 0 when x goes to 0. Or
Yes, that is the precondition here for this construction to work. And here, this is always, I should perhaps have mentioned that. Here, this is always the case because, let me see. Because, we said that, we assumed that this thing has decreasing exponents, so the first exponent in this thing will be less than e. And here we essentially have the first exponent of x's minus e, so the result will always be negative. So this ensures that it always works if we plug in this thing into the power series expansion. And as I told you before, it doesn't work for all functions, because if we have logarithms and exponentials, we can get singularities, and then it doesn't work out that easily. And the question is, what do we do then? And the answer is, as you already said before, we have to be a bit more liberal about what we allow. So just allowing powers of x doesn't get us very far. We can't analyze any interesting functions with that. And essentially what we allow is any products of powers of something we call an asymptotic basis. For instance, you could have an asymptotic basis e to the x, x and ln x, and then you have monomials that essentially look like this. And then you could, for instance, encode this very small expansion here in this way. So you have here the coefficient 1, and the exponent of the e to the x is 4, and the other exponents are 0, and then here in the end you have the same thing. Yeah. So, is that clear? Okay. And alternatively, you can view this hierarchically. So you can essentially say, I look at this thing as an expansion in e to the x, but the coefficients are no longer just real constants, they are themselves functions, but these functions now have, the coefficient functions have an expansion in a smaller basis. So essentially, you can say that if you have a basis b prepended to bs, then an expansion with respect to that basis is just again such an infinite list where the coefficients are again functions, but with respect to the basis bs. It's a hierarchical view, and then essentially it would look like this. So very similar. The difference is now that the coefficient is essentially at the end. So an expansion with respect to the empty basis is just a real number, a real constant. And and you can still read off limits relatively easily, because now the leading term is essentially some constant times product of powers of the basis functions. And I should have mentioned that. So one thing you require of an asymptotic basis is this property that any positive power of this thing will be greater, will dominate any power of this thing. So essentially, it suffices to look at the leading terms unless they are equal. So if you want to know the limit of this thing, you can essentially just look at what is the first non-zero exponent here in the list. And if it's negative, then the limit is 0, because the entire thing has to go to 0. And if it's positive, then it is just the sign of this constant times infinity, because the entire thing goes to infinity. and if all of those are 0, then it's just the constant itself. So you can still very easily read off the limit. And so what has actually changed concretely? So before we had this very simple view where an expansion was like a list of pairs of real numbers. This doesn't work anymore. Now we have to first define what a basis is. So a basis is a list of real functions from real to real. And we implicitly also assume that they always decrease in growth in this sense, so I specified before. And that they also all go to infinity. That's also something we assume. And now our expansions are essentially like a generalized algebraic data type. So we have an expansion with respect to a basis, and the basis is kind of always implicitly part of the expansion. And so an expansion with respect to the empty, with respect to the empty basis is just a real number, and an expansion with respect to a composed, a non-empty basis is again an impossible infinite list of coefficients and exponents, but the coefficients are now again expansions of a smaller basis. That's just what it means. And we can still define negation very easily. We say a negation of a constant is just minus the constant. I should say const of minus c, of course, here, sorry. And a negation of an expansion is essentially just like we had here before. The only difference is now that negating the coefficient is again a recursive call to the negate operation. So it still works out pretty much the same thing. Question?
I'm thinking that whether the EXP constructor should somehow take an R as a real number as B or something.
Come again?
I have trouble like parsing the EXP constructor of the data type.
Yes.
Shouldn't it take a real number as B?
Real number is B.
Wait,
So we were wondering what little b is there.
yeah.
Sorry?
Yeah, what is little b?
This it's the first basis element. It's a function.
But is that a data type declaration or what? I mean,
It's not in Isabelle data type.
Yeah. You cannot do this in Isabelle. This is like Hesse has these generalized algebraic data types, and this is like a very nice way to write down what I mean. So we cannot do anything like that in Isabelle. And in Isabelle it looks very different, but this is like the idea if you strip it down to the very core. In Isabelle, I essentially, I'll just say that for the benefit of the Isabelle users here, I essentially emulated these generalized algebraic data types with type classes, which is kind of a hack, but it works out very well.
So I really have no idea what all that is meant to mean anyway.
So essentially it means that X is essentially a type that depends on a term, and the term is a list of basis elements. And so you have like a type expansion with respect to an empty basis, and you have something like expansions with respect to the basis e of x, e to the x, and x, something like that. You can essentially just recursively define what these expansions look like. So for instance, like you could say essentially if you have just like the number 2, then this is already an expansion with respect to the empty basis. And if you have something like x plus x to the minus 1, then this is an expansion with respect to the basis x. And then something like e to the x plus ln x, for instance, that would be an expansion with respect to the basis e to the x, x, ln x. That's the idea.
Can you miss out the x in the middle of it?
Well, in theory, yes, but in practice, all of my bases will always contain the identity function. Okay.
So that real number is b, although it's not said anywhere.
No, b is not a real number.
Oh, it's
B is a function. B is a real function.
I see.
It's like a basis element. And a basis element is always a function, like e to the x, ln x.
Yeah, it would be interesting to see the interpretation.
What do you mean by interpretation?
How do you? I mean, if you want to interpret the x as some kind of I have an x data, an element, and want to interpret it now as a function from real to real.
Yeah, that in general that is not always possible. For all the grid-based series, that is possible. Is it? I'm not sure. Well, essentially, I think a large number of the series that I generate will actually be convergent, and then it is possible.
Yeah.
And then it's just like the interpretation is relatively easy. It's namely just essentially so eval of c1 of x plus this thing is just at x is just the sum overall ci of e to the e, and this is convergent then. But in general, it's not always convergent, and then it's a bit more difficult. So essentially, what I do is I kind of in Isabelle I explicitly store the function that this that an expansion corresponds to within the expansion. So essentially, this x constructor has an additional value here that stores the entire function, so that I kind of never forget what function I was actually looking at. And yeah, and so the main part, which I think I'm not going to show here, is essentially I have a kind of a relation between an expansion and a real function, and this relation just specifies this property that I showed you before, that if you cut it off after a finite number of elements, then you get an approximation of a certain order. And this is the connection that I make in Isabelle between functions and expansions. And what I show is that all the operations here, like negation and addition and multiplication, that they preserve this relation. And this relation itself is, you can specify it very easily as a co-inductive predicate, and so you can use co-induction to show that this is the case, that's preserved. Any question?
No, I just want to say that if I eventually got it.
Okay.
So maybe you can, I'm not sure. I think no, actually, active syntax might be better if you want to follow the Haskell.
Isn't that active syntax?
No, like you can mimic. No, it's not. Okay,
Okay, so this is the thing is I'm not very well versed in dependent types, so this is what you can already do in Haskell, more or less. Well, not really numbers, of course, but apart from that, you can pretty much write this in Haskell. So I hope that this would be illuminating enough. But I think that if you've never seen Haskell style generalized algebraic data types, it might not be that helpful. Okay. So yeah, and now we can also do the logarithm, and it works very similar to the multiplicative inverse. So we again write f as a sum of this leading term and some g of x, and here we require that the c of x is again non-zero. So by non-zero I mean it is eventually non-zero, and then we can rearrange it like this. Assuming that the logarithm is indeed well defined. So actually we don't just require that it's eventually non-zero, it has to be eventually positive, because otherwise the logarithm would not be well defined. And then we can rewrite it like this, and then we can again rewrite it like this, and now we have we're happy because yeah, this thing here I'll talk about later. No, sorry, this thing is just a recursive call essentially of our logarithm operation. So the c of x has an expansion with respect to a smaller basis, so we can just recursively call the logarithm operation. And this thing here is again, this function has a power series expansion, so we can again substitute into the power series. And so the only question is, what do we do about this thing? And the answer is simply, well, L and x has to be part of our basis, and if it isn't, we have to add it to our basis. So in general, of course, we don't have x here, but we have some basis element b of x, and then we just have to essentially look whether L and b of x is already expandable, and if not, we have to add it to our basis. And essentially, we also know that we have to add it to the back of our basis. That's another invariant. Yeah, never mind. But yeah, that's essentially everything there is to know about the logarithm. And the exponential is a lot more complicated, so it's a lot of case distinctions, and you can get ugly new basis elements like this. So the logarithm was very nice because essentially you always got just a logarithm of a basis element you already had, so that's very easy. In fact, actually the algorithm is such that all the logarithms you get are iterated logarithms of x, so it's very nice. But with the exponential you can get really ugly stuff like this. And yeah, when I first implemented this in ML, I had a huge number of bugs and it took me ages to figure it all out. But of course, luckily, it's not a big problem because when I have a bug in my ML code, it doesn't mean that I prove something that's wrong. It just means that the Isabelle kernel is going to blow up in my face if I try to actually run the code, because the theorems won't match up and it'll just complain. So, yeah.
Sorry, this one is like x of x times x of 1 over x. So you could break it down into smaller bases.
Yes, you could actually do that, but the problem is you can also have something like e to the x to the 1000 plus x to the 999 plus blah blah blah.
I see this can be arbitrarily complicated. I just wanted to say that this one example is maybe not so bad.
So I visited Joyce van der Hoeven in Paris and talked to him about this because he, I think, was one of the people who essentially came up with this idea. And he, I think, always does this thing that he always kind of demands that no such terms are present, and he would essentially expand this thing until here. But I haven't quite understood yet why, essentially you can have degenerate cases like this, and then it might be a bad idea. So I still have to ask him what he actually does in such cases, but essentially I didn't worry about that because I just essentially I take the elements, the new basis elements like they come without making any attempt to make them any prettier, because in general I think it's not possible. And it worked out well enough like this. Okay, so what does it look like in Isabelle? So essentially I have something like this. So I have a data type, alpha multiseries. So yeah, I should mention that these hierarchical series, they're called multiseries. And it has one constructor and one value for the is the expansion itself, and the other constructor is the other value is the function that I was going to expand, because that's, as I said, in general it's this is like not a one-to-one mapping from functions to expansions, and like in most cases it is, but not always. And it's just a lot nicer if you always kind of explicitly have the function lying around that you were going to expand in the first place. And so the idea is that this is essentially one step in the expansion hierarchy, and if you have an expansion of order 3, meaning you have 3 basis elements, then you just write real ms, ms, ms. And you can just stack it arbitrarily. And all this kind of these recursive algorithms that I showed before, they are essentially implemented with type classes. So I have a type class multi-series that provides all these operations, and essentially the termination of the recursion is guaranteed by the type system, because I always strip away one of the MS type constructors. And it's kind of a hack to emulate these generalized data types in Isabelle. I could have done it without that, just with a single data type, but I tried that, and then the proofs got a lot messier, because then I had to have nested recursion or a mutual recursion, and everything just got a lot more ugly. And so I did it this way. And I already mentioned this before, but essentially all the operations that I showed, like addition, multiplication, power series, can be defined co-recursively with just more Bichet's and Title, I think, with the co-data type package, and you can prove them correct with co-induction. And by correct, I mean, as I said before, I have this co-inductive predicate that specifies, okay, this is a well-formed expansion, and it is really an expansion of this particular function, by which I mean that if I cut off the expansion after a certain number of terms, and I get something with an error, blah, 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 and so on and so forth. This can be specified very naturally as a co-inductive predicate, and then you can just show that the co-inductive predicate is preserved by the operations with co-induction. And it's conceptually relatively simple, but there are of course a lot of technical details that make this very ugly sometimes. But it works out fine, and then the end question is, how do we actually use this to prove stuff? And so the first problem, one big problem here is that we have to compute expansions, right? Which I mean, okay, so far we can write down these expansions as terms in HOL. So we can write something like, the expansion x plus the expansion x squared, but how do we actually then get Isabelle to compute what the result of that is? And Isabelle has, of course, several tools to evaluate terms, but always strictly. So this only works when you have a kind of a normal form, but we don't have this here because our lists can be infinitely long. We cannot just compute a normal form. We need a kind of lazy evaluation of whole terms. And so yeah, that's what I had to do. I had to implement a lazy evaluation engine for whole terms. And for this I read this little framework where you essentially say, okay, these are the data types and coded data types I want to support, and these are the constructors that they have, and these are the functions on data types and coded data types that I want to support. And the functions are defined by function equations of form, like this form. And then the framework essentially, it applies rewriting until it can decide, for instance, pattern matching. So you can ask, does I have this pattern, does this match to this term modular rewriting? And so the framework will apply the function equations until it can decide that, and then give you the result. It can also compute a head normal form, so it can compute the leading term of an expansion, for instance.
Is this now run through the simplifier, or is this for the code generator?
This all runs through the simplifier.
Okay.
Would it be such a pain if we just had, or if you just had a construct which takes an expansion and a natural number and unravels it that much, and then you have your goal and you say, unfold this logarithm 3 orders far and this one 5 orders, and then you can let the eager evaluation do the rest. And if that doesn't help, then you try other numbers. And here it's all automatic, but I mean this final step is maybe not so big, because normally they just say, yeah, we unfold this to the second order, and then it all goes.
I could have done that, but then I would essentially have to prove a lot of theorems to relate the infinite sequence to like its finite prefixes, and then combining all the prefixes. So I'm not sure if it would have made things easier.
Yeah, but what confuses me usually with the data type package sets up the rule that you only evaluate a co-recursive function when you are under projection. Like,
yeah, I don't know.
So when you just run the simplifier, I thought this should work. As far as I understand.
Yeah, but then the question is, okay, so I have some arbitrary term that is an expansion, and I want to know, is it empty or does it have a leading term? And if that, I guess, what is the leading term? So then I probably would have to run this several times, right? I would first have to run it once to determine whether it's empty and so on. So I don't know if that's really a good idea.
Okay.
So yeah, and essentially the framework produces a theorem of the form original term equals the reduced term. And the big problem is that it doesn't support sharing at all. So if you have Haskell, essentially in Haskell, if you have if a variable on the left hand side appears several times on the right hand side, then after the reduction, all of the occurrences on the right hand side will be the same value in memory. So if you reduce one of them further, then all of them get reduced, and you don't have to do the work several times. And I really wasn't able to figure out how to do this in Isabelle, because it's not enough to just compute the actual result. I always have to produce a theorem like this, and I couldn't really figure out with a reasonable amount of effort how to produce theorems when you have sharing in the background.
Okay, you said the computer algebra system can do such limit evaluations.
Yeah.
So do they have lazy evaluation inside?
Yes.
Or they have.
They pretty much use that. Yeah, I mean you can usually emulate it with like some kind of closure or something. So I think that's what they usually do. Like I think I've seen Maple code do this, and they have some concept of lazy sequences. Okay. So another big problem with evaluation is you have to compare real numbers, and I mean, in most cases I found that the comparisons you have to make are something like 1 is less than 2, and so it's no problem. But in theory, you can have things like square root of 2 is less than 1 plus square root of 3 or something. So this is already a bit more complicated. And I mean, in general, you could have any kinds of constants appearing there if they appear in your original term. So this is relatively difficult to solve. And I think if you have exponentials and logarithms and irrational numbers in any combination, then there is already no known algorithm to solve these problems. So it's still an open question. And the question is, of course, what do you do about it? And an even bigger problem is that I always said that, okay, we assume that the leading coefficient is non-zero. The question is, of course, what do you do when it is 0? When it is like an identically 0 function, like you have a leading coefficient that is x minus x. I mean, that is, of course, very obvious, but you can imagine more difficult things. And essentially what you have to do is you have to find out whether a function is identically zero. And that's also a very difficult problem. It's, well, it's actually, I think it's, in theory, it's equally difficult to this one here, but of course in practice it's even more difficult. And yeah, they might even be undecided, but it's not quite clear yet. And well, if you allow complicated constants, then they will be undecidable, of course. So the question is, what do we do? And I did a very, very simple heuristic approach. I essentially just applied Isabelle's automation on the goal to determine the signs. So as I said, okay, just can you prove that one of them is smaller than the other? And if yes, then everything is fine. And if you cannot, then you just give the user an error message. And then the user might have to prove additional facts and then to make the automation figure it out. And if for the identity zeroness test, I essentially apply the automation, and if it says if it can prove that it's identity zero, then I just use that. And if it cannot prove it, then I just pretend that that it's non-zero. And this doesn't cause any soundness problems, so I don't actually need the fact that it's non-zero. I can just, but if I assume that it was non-zero, but in reality it was zero, then my algorithm will run into non-termination because it will try to reduce some. It will try to find a non-zero leading term of something that is identically zero, and that can of course never work. Yeah, and as I said, if the automation really does run into problems, then the user might just have to supply some additional facts to make it work out. And this very simple approach works surprisingly well. So I've run into some examples where you really had to prove some simple stuff before it works, but I never ran into any big problems where you had to prove something very complicated or something. So it was always really simple stuff. So yeah, so I ran into the problem where you have like square root of 16, and with the existing automation, Isabelle couldn't reduce that to 4. So I had to either prove that by hand, or then I wrote like a tiny simplification procedure that takes care of these things, and then it works again. So in practice, most of the problems that you get here are very, very simple, so simple that the automation can solve them. And in principle, of course, you could use additional backends in the future. Like you could say, okay, if Isabelle can't figure it out, just talk to Mathematica, and if Mathematica, and then you don't trust Mathematica, so you would have to give this to the user to prove afterwards. Yeah, and at this point we have all the ingredients we need, so we can parse and pre-process the input expression. Then we compute the expansions. We just go bottom up. So we start with the leaves of the expression tree, and then we just build up more and more until we have an expansion for the whole thing. And then we use the evaluation framework that I just explained to trim the expansion, determine the signs when we have to, and in the end we just trim it again and determine the leading term, and then we can read off the limit. And with some pre-processing, we can then essentially automatically prove statements of the form f goes to some limit, or f is asymptotically equivalent to g, or f is element some Landau symbol of g. And we can do this not only for x going to infinity, but essentially for x going to any real number and positive, negative infinity. And the functions themselves can be built from basic arithmetic, and also logarithm, exponential, minimum, maximum, power, absolute value.
There's no difference if I go from left or from right to any?
Yes, you can also do that. Actually, you can only do that, and if you want both sides, you have to simulate it by running. Well, it automatically does that by running it from the left and from the right. Yeah, and you can even do trigonometric functions as long as the arguments are finite. So you can do something like sines of 1 over x for x to infinity, but you can't do sine of x for x into infinity, because you get oscillations. And then, for instance, like a simple thing you can prove with that automatically is you can write 1 plus 1 over n to the n goes to Euler's number, which is a well-known fact. It's completely automatic. But you can also do it something a bit more tricky. So you can also prove that this thing just goes to the exponential of y. And here, if you just run xlog asymptotics, it will say, okay, I need to determine whether y is 0 in order to compute the leading term. And I couldn't prove either. And then you have to do a case distinction manually, saying, okay, the 0 case is easy, so it's handled by the simplifier. And if it's non-zero, then I just invoke xlog asymptotics, and now it works, because it can determine whether y is 0 or not. Or another example related to what you said before about polynomials and exponentials. So you can show that any polynomial is element small o of any exponential if the base is larger than 1. It's also completely automatic. And again, we see that this thing is actually redundant. You don't really need that. But if you don't have that, then again, the thing will complain about not being able to determine the non-zeroness of something. So yeah, you need that. And also, I showed you the acrobacy example before. So this is an even more general version of the acrobacy thing that I showed you before, which has even more free variables in it. And now this is also mostly automatic. And the semi-automatic part is essentially that you have to additionally supply this fact, which just says that if you multiply a negative number and a positive number, then the result is negative. So if you don't have this, then essentially you will get an error message saying pretty much that it was unable to prove to determine the sign of something of the form a times b, where a is negative and b is positive. So you just have to figure out that it needs this additional rule, and then again it's automatic. And remember, like before, this was 700 lines of proof, and now it's just oh yeah, and it works in 0.3 seconds. And just to give you an impression of how big the intermediate terms get here, so the expansion, if you unfold the expansions only as far as you need them, the terms that you get in the whole terms have a size of several megabytes, and it still works in like fractions of seconds. So I think that's really shows that Isabelle's internal processing is very fast. And yeah, so surprisingly, all the examples that I tried took no more than a few seconds, and free variables, as long as they don't affect the result too much, are no problem at all. Yes?
So do you have something like reflection in your method, or
No.
just purely simplifier?
It's all, I only use to simplify. Everything goes through the kernel.
Okay.
Yeah, and yeah, it's a problem. So, of course, so if you have a lot of cancellations, then the performance can degrade very quickly because the terms get huge, and the addition and multiplication algorithms themselves are also quadratic, I think, if not worse. But in practice, you don't end up in this kind of situation very often. So usually, if you have like the first 3 or 4 terms or something, it's more than enough. Sometimes, in most cases, I would argue that you have no more than 0 or 1 cancellations. So yeah.
So the prime number theorem proof has some pretty horrible limit calculations, doesn't it? Does this apply to any of those?
Real or complex?
Good question.
Because I cannot do complex asymptotics at all. I can only do real asymptotics.
Yeah, that's probably complex.
So I would have to have.
I would honestly have no idea.
I would have to look at the concrete examples.
Well, it's the complex. You're talking about the complex.
Yeah. So those limits, are they complex limits? I don't remember what they're taking limit of anymore.
Well, a complex. When you talk about complex asymptotic, anyhow, you take a norm and turn it into a real, so somehow.
Yeah, but you also have like the direction of approach. You have infinitely many directions in which you can approach, and that complicates things. And also, when you have complex asymptotics, you can get oscillations. Like if you have an exponential of something that is even of a linear term in a sense, then yeah, you can get oscillations, and that you can handle with this approach. So complex asymptotics are a completely different thing than real asymptotics, and so I asked Joris, who I think is kind of an expert in these things, and he said that essentially there is no known approach to tackle complex asymptotics. It's all just heuristics. But real asymptotics, I think, is very well understood. So there are some things that you can do with sines and cosines, even with oscillations, but it gets a lot more difficult than what I presented here, and I'm not sure if I will probably not try to tackle this. Yeah, okay, so also, as I said, the zeroness and sign tests that if they don't work automatically, then you have to invest some work to figure out what went wrong. So that maybe I could improve that a little bit. And you have to do case distinctions, or sometimes when you have free variables in there, as I said before, you sometimes have to do case distinctions in order to help it along. And the formalization itself was very ad hoc in a sense, so I always had this very concrete representation of these series, and I didn't worry about things like, are they grid-based or anything. So there is this very, very complex and nice algebraic hierarchy of these series. Joris van Hoven calls them the trans series. but I don't understand it at all. It's a very, very complicated matter, and I don't think there's much of a reason to formalize them in Isabelle if you only want to do limit computations with them. So I think this is like a very ad hoc and practical approach. But of course, you could do it in a more abstract, nice way, I suppose. But it would probably be a lot more work, and I would have to understand it a lot better. And so all in all, it's about 500 lines of Isabelle theory and about 3,000 lines of ML code.
5,000 or 500?
Sorry, 5,000. And the thing is, of course, you don't have to trust the ML code. So if the ML code makes a mistake, then the Isabelle kernel should catch it. So you only have to trust the kernel. In this case, you don't have to trust my ML code, which is good because it has a lot of bugs in the beginning. I invested about 5 months in total, I would say. And as I said, the implementation was pretty tricky to get right. So I would argue that if I were to implement this in a computer algebra system, if I, for one, had implemented this in a computer algebra system, there would probably have been a lot of bugs in there at first. And you would have to do a lot of testing to get this right. So it's nice to have having a theorem prover where you can just trust the results to some extent. And so, as I said before, Dominik Grunz implemented a similar algorithm in Maple. And apparently, someone said to me that it's now part of Mathematica as well. But in his PhD thesis back then, he essentially compared his new method, which was like the systematic approach, to the previous things that computer algebra systems did, which was pure heuristics. And he found that pretty much all the computer algebra systems in use back then, that was about 20 years ago, gave wrong results for many of his test cases. So it was a complete disaster. But nowadays, if you try it again, some of them have completely died off. But if you try it with modern computer algebra systems, like it works relatively well. So Mathematica and Maple, they give correct results in all of them very quickly. I'll say a bit more about the other one. So essentially, he had a collection of test cases, and he supported a few more functions than I do. But there were 23 of his test cases that I also support, and I tried them, and all of them worked automatically without any kind of additional work required from me. And the maximum time was about 1.7 seconds, and the median about 0.3 seconds, which I think is very good. And of course, as I said, Mathematica and Maple can do all of them very quickly and correctly. They're quite sophisticated. But the other systems I tried couldn't do all of them, so they just failed on some of them. And Maxima and Sage actually gave a wrong result for one of the examples that he published 20 years ago. So they claim that this thing here goes to 1 when in practice it goes to E. And I have no idea why they do that. I should probably report this as a bug at some point. So how well are we doing? I would say, the Isabelle approach is actually not that much slower, even though it goes through the entire Isabelle kernel. So in all of those examples, usually Maple and Mathematica were a bit faster, but not that much faster. And as I said, I never took more than 0.3 seconds. I usually didn't take more than 0.3 seconds. And also, all the computer algebra systems I tried couldn't do the acrobacy example, not even the easier one, because as soon as you have 2 free variables in there, they usually just don't give you any result anymore. And I have no idea why that is the case. And it's also completely impossible for me to debug these things because they are so intransparent. They don't tell you why things go wrong. They just don't give you a result. And I asked on Math Overflow, I think, and people there was just yeah, I don't know. I noticed as well that it doesn't do free variables very, very well, but I don't know why. But of course, in general, one must of course keep in mind that Mathematica and Maple are much better, both in their speed and also in the scope of functions that they support. So there are a lot of things that, of course, these systems can do, and that the Isabelle thing can't. But of course, you have to trust the implementation. So they could have bugs in there. They did have bugs in the past. So when you get a result, it's probably right, but you can never be quite sure. And so the bottom line is, Isabelle isn't a computer algebra system yet, but I hope that we're getting there. As future work, so I tried to also add some support for the gamma function and the polygamma function and the arctangent. And in theory, this is possible, but in practice, it got a lot more complicated than any of the other stuff, and also a lot slower because the basis elements that you have to handle get more ugly, and you get more cancellation. I don't know, it's pretty messy. And as I said before, I cannot handle oscillating functions at all at the moment. I have some ideas how to at least partially support oscillating functions, which I might try at some point. And the user interaction for the zeroness test isn't ideal at the moment, but in practice I think it works quite well for most examples. And yeah, what I could do, I have to prove that. So I don't think we have time for any demo anymore. I'm afraid I used quite a lot more time than I thought I would.
Yeah, there were more questions.
Yeah.
So interesting.
Okay. Well, any more questions?
Can you somehow extract rigorous bounds on
No.
the thing that you?
No,
is it
no.
like it's really not possible, or?
I have no idea. I think the entire approach is very much not geared to that. So I think it's just, I don't see any way to add a bound extraction to that at all. So maybe, I mean, I'm hardly an expert on these things, so maybe it's just that I don't see it, but I wouldn't know how. So I think maybe intuitively it's a very powerful and general approach, and there's a price you have to pay, and the price is you don't get concrete bounds. That would be my intuition.
I guess you would get them. I mean, the Stilter definition has like this eventually, so that gives you, that embodies a function. So if your proof is constructive, and I think all your proofs are, so in principle you could just like extract a program.
I'm not sure if they're definitely not constructive in the sense, like they might be morally constructive in a sense.
But are you using like axiom of choice in your verification? I think not.
Even if I don't use it directly, there are so many Isabelle tools that use these things all the time because they're there. So I think, like formally speaking, it will not be a constructive proof at all. It might be that it's a morally constructive proof in the sense that I really could provide explicit witnesses for these things, but I think also Isabelle very much isn't really geared towards that at all.
But the question was whether in theory you could.
Yeah, in
it
theory,
would
I don't
seem
know.
that at the end of the day you are plugging these things together and.
Yeah, maybe. So I don't know how much classical reasoning is really going on there in these proofs because I never really thought about it, and I'm just not kind of educated to think about these things in a constructive way. So
I mean, sometimes you get these things like there's this set that goes, sequence that goes down and is bounded, and therefore there exists infimum, that sort of thing. But maybe you are not using that sort of funny principle.
I really cannot say. But even then, I think it would be very questionable whether the bounds that you get out are useful at all. I think that you'll probably find that they are much higher than they would have to be.
So I still would like to bring up this question again with this by hand evaluation. I mean, not that I'm propagating this now, but like suppose you take this acrobacy thing and you replace all your terms with say order 4 asymptotic just by a lemma that allows you to replace one by the other.
Yeah.
Would it then just go away with an ordinary Isabelle tool?
Probably.
Wait, what was that?
Like if you just kind of, if you pretend that these are infinite sequences, but you just take like the first 4 terms of every expansion, and
And leave the whole remainder there, of course. That you have to do, otherwise
okay,
it's
well,
unsound.
then you would have to write things down in a different way, I would imagine.
You have some kind of memorization.
Well, yeah, okay, you could just kind of hide the remainder term behind some definition and pretend it's a variable and then do the expansion. Yeah, you could probably do that.